All right, so we're going to go ahead and get started. Our next speaker is Sarah Horst, and she's going to tell us about planetary atmospheres.
Hopefully. Can everyone hear me? No, this is not. You can hear me okay? Wow, the sound is really weird up here. Yeah. Okay. If you suddenly lose the ability to hear me, can you just like wave your arms at me? Okay. Oh gosh. Titan doesn't look very pretty with the lighting in this room. That's okay. We'll survive. I'm going to talk about planetary atmospheres, which I think is maybe obvious. The session is about remote sensing, and I'm going to kind of go back and forth between remote sensing and spacecraft observations, although we do a lot of remote sensing from spacecraft as well. So hopefully everything will make sense. That's the goal anyway. So I wanted to take one step back first and just kind of remind everybody the questions that we're trying to answer when we're trying to understand planetary atmospheres in general, the chemistry of planetary atmospheres more specifically. And so, you know, at the very biggest kind of level of stepping back, the questions that we're interested in answering are, you know, how did we get here? Are we alone in the universe? Are we alone in the solar system? And you know, zooming in just a little bit, specific to planetary atmospheres, one of the questions that I'm most interested in attempting to answer is, what role do atmospheres play in the origin of life, maybe in the evolution of life, and also now that we're starting to think about things like James Webb, what role are atmospheres going to play in the detection of life and our ability to actually find life somewhere either in the solar system or elsewhere in the universe. And so that's kind of the zoomed out picture of what we're interested in. And I'm going to focus a lot on Titan today, which is the largest moon of Saturn, in part because it's one of the places where we have the most information in terms of starting to try to answer these questions. And so I think it's a really great example to look at. So one other thing to think about too, more specifically, is why does atmospheric chemistry matter? So why do you have someone who studies atmospheric chemistry of other planets here today talking to you? And it matters a lot. And the reason for that is that atmospheric chemistry will determine the chemical composition of the atmospheric gases. This is important for lots of reasons, but one of the reasons it's important is that if we're chasing biosignatures, we need to know what the atmospheric chemical composition is on its own. It determines whether or not there's particles. Those could be clouds, those could be photochemical hazes, those could potentially be spores or bacteria, depending on what's happened on that planet. Certainly many of our particles in our atmosphere are composed of those types of particles. How many are there? What kind are they? Where are they located? It determines how radiation moves through an atmosphere. And it determines the atmosphere and surface temperatures. And frustratingly, all of these things are connected to each other because there's a lot of feedbacks involved. And so as photochemistry changes the composition of an atmosphere, that changes what photons are available to drive the chemistry in the first place. And so we have to actually understand how all of these things are interrelated, and that's very challenging. And so those are kind of the big picture questions that we're looking at answering. And one of the best tools that we have for starting to think about these questions is remote sensing. Because if we don't know what the atmospheres are made of in the first place, then all of the rest of these questions become irrelevant because we don't even know how to start thinking about them yet. So I wanted to step even farther back in time for Titan, just to remind everyone how we start when we start studying planetary atmospheres, or in this case, the atmosphere of a moon. So the first step, which sounds ridiculous, is that we have to know it exists. And we're kind of following this pathway again now with extrasolar planets, which is why I wanted to start here. And so this is the first time that we knew that Titan existed. Cassini-Huygens discovered Titan. Once we know that it exists, if we want to study an atmosphere, we need to know whether or not it has one first. And this is, again, a place where remote sensing can go into play. Luckily, this one at least looks a little bit better. So the first mention of the possibility of Titan having an atmosphere was actually in 1907. This is a drawing that was made that indicated there might be some limb darkening. And so if we look at a planet or a moon across different wavelengths, or potentially if we can actually resolve the disk, and we see that the middle of it looks different than the outsides of it, then that's a pretty good sign that there is gas surrounding the planet. And so this was suggestive of an atmosphere, but not conclusive. And so our first conclusive evidence that Titan had an atmosphere is shown here. This is our first proper spectroscopy of this talk, and it may almost be our last. And this is a spectrum of Titan that was taken by Gerard Kuiper in the 1940s. And this shows that, in the near infrared, there's a whole bunch of these spectral fingerprints that have come up a bunch of times already today. And in this case, this is the signature of methane. And this paper is titled Titan, a Satellite with an Atmosphere, and I've always felt that there's a piece of punctuation missing at the end of the title of this paper. I don't know if it's a question mark or an exclamation point or both, but this was the first time we realized we have a moon in our solar system that has an atmosphere. We didn't know anything else about it at that point, but we knew that there was methane. And this, again, is kind of the process that the extrasolar planet community is going through right now. So they're finding these planets, they know they have atmospheres, and then starting to try to figure out what molecules might be present. And at first, it's frustratingly slow, one molecule at a time. But I can assure them that changed for us quite rapidly once we had the technology. So we knew there was methane, and Titan and this setup just do not work very well together, although it's maybe representative of what the lighting is like out at Saturn. So once we knew there was methane, then immediately we thought this might be a really interesting system. We know that there's a moon that has an atmosphere, which is weird, and so Titan was one of the main targets of the Voyager spacecraft. And in fact, it's because of Titan that both Voyager spacecraft didn't go to Uranus and Neptune, because they wanted to get a closer look at Titan, and that changed the tour. So when Voyager got there, this is what Voyager saw. I always joke with people that you can reproduce this at home yourself with an iPhone and an orange, and you will get approximate. Okay, see, we're going to do this. We can do it together. I assure you, we will survive the post-lunch slump. And the thing is, if you did that, you would get about the same amount of information from having done the exercise, although you would have a higher resolution picture than this one. The good news is that Voyager was carrying more than just cameras, and Voyager was carrying an infrared spectrometer called IRIS. And immediately when the IRIS data came back, it became apparent that Titan's atmosphere was even more interesting than we had thought. And so from this beautiful infrared data was the discovery of a number of organic molecules in Titan's atmosphere. So there was propane, in case you wanted to, have everybody over for a barbecue this weekend. There was hydrogen cyanide, in case you don't like your friends very much that you're inviting over to the barbecue. Ethane, acetylene, a number of other organic molecules. And so immediately Titan became this really important target for exploration, because we had all this organic chemistry happening in the atmosphere that we were just beginning to try to figure out how it was happening. But then we couldn't see the surface, because between the thick haze, what turned out to be quite a thick atmosphere, and also methane, which absorbs very strongly in a lot of wavelengths that we're looking at, we couldn't see the surface. And so there could have been Titanians jumping up and down and waving their hands at the Voyager spacecraft, and we would have had no idea, because we couldn't see down to the surface. And so this was really frustrating for everybody, and we really wanted to go back. I have no idea what the next slide is. We'll see. Okay. This is going to be a little bit of a choose-your-own-adventure situation here, because my slides are in a different order than usual. Before we went back, though, it turned out that remote sensing was going to be hugely important for us in understanding a lot of other aspects of Titan's atmosphere. So one of the things that's really interesting is that clouds in Titan's atmosphere were first detected using spectroscopy. And so there was this particular window in Titan's atmosphere where there had been a number of observations, and you could see that there were leading, trailing asymmetries. So there was some kind of surface albedo variation. But after looking at that enough times, you kind of get an idea of what that's supposed to look like. And then all of a sudden one day, there was this huge brightening event in that window that couldn't be attributed to a surface variation. It had to be a cloud. And so this is our first detection of clouds on Titan, and it's very unsatisfying. When I show this to the undergrads, they're like, "That's a cloud?" I'm like, yeah, that's what a cloud looks like in a spectrum. So that was really exciting. A number of other telescopes, ground-based and Earth-observing telescopes, were also being used to look at Titan during the 80s and during the 90s, finding new molecules that we didn't know had been present in Titan's atmosphere, including benzene. Benzene was discovered in the late 1990s using the Infrared Space Observatory. That was now and still is one of the heaviest molecules that's ever been detected in a planetary atmosphere from remote sensing. And there's a number of reasons why, which have been mentioned already today, and I'll just emphasize again in a little bit. So it turns out that Titan's really unique in the solar system. From Voyager data, we knew that the surface temperature was quite low, about 94 Kelvin, but that the pressure at the surface was about 1.5 bar. That means that the density of Titan's atmosphere at the surface is about 4 times that of Earth. If you somehow find yourself there, you could cut wings out of cardboard and tape them to your arms and fly by flapping your arms under your own power. Which means that Titan is one of the best places to fly in the solar system, should someone perhaps, I don't know, want to send a dual quadcopter called Dragonfly there. I'm glad some of you appreciate me, that's good. Some of you don't maybe know what I'm talking about, but that's okay too. And so Titan's the only moon in the solar system that has a substantial atmosphere. And so one of the things that we found out from Voyager is that there's about 2% methane in Titan's atmosphere. From Kuiper, we knew there was methane, but we didn't know how much because the spectra weren't good enough to actually quantify the amount of methane. But from Voyager, we were still unable to tell how much nitrogen there was. So on here, I'm telling you there's 98% nitrogen, which is true, but we didn't actually know that from Voyager. We could only tell what the pressure was because of the pressure broadening of these lines, but we didn't know if it was all molecular nitrogen or if there was some contribution from something that's very hard to see from remote sensing, like argon, for example. And so that was only answered by sending a spacecraft there. And so that's one of the challenges that we have with trying to study planetary atmospheres using remote sensing alone, is that there are a number of molecules that actually hide themselves very, very well in plain sight when we're trying to use remote sensing as our only tool to analyze these places. From that methane, we have photochemistry that results in a bunch of those molecules I showed you already. So we get this hydrogen cyanide and propane and all of these other things. There's also some oxygen-containing molecules, which I'll come back to in a little bit. The most abundant of those is carbon monoxide, which has an abundance of about 50 parts per million. And the detection of carbon monoxide is actually one of my favorite remote sensing stories in Titan's atmosphere, at least, because CO2 was discovered by Voyager in that iris spectrum that I showed you earlier. And as soon as the data came back, everyone thought, there's oxygen-bearing molecules in Titan's atmosphere? Or if there's CO2, there's almost certainly CO. And so, within a few days of having those Voyager data on the ground, they'd pointed a telescope at Titan that could look in the microwave, and they'd discovered carbon monoxide in Titan's atmosphere. And so it was just as soon as we knew what to look for, it became really easy to find. It was just that it hadn't occurred to people that that molecule might be there. And that's a really consistent story across the years for our use of remote sensing to interrogate Titan's atmosphere. So Titan's atmosphere is really unique in the solar system because it has this reducing atmosphere with all of this methane, but there's also some carbon-bearing molecules. And so this thick haze that comes from all this photochemistry has the potential to incorporate carbon, nitrogen, hydrogen, and oxygen, which are important for a lot of the molecules that have already been discussed today. And so I won't keep emphasizing that point. So the next tool that we used to study Titan's atmosphere was the Cassini-Huygens spacecraft. That was a joint NASA-ESA mission. Huygens is the probe, switch this way, which is shown here, this giant gold circle thing. Some people don't realize the scale of Cassini, so I always try to remind people that these are humans. So Cassini's not a cute little Mars rover. It's about the size of a school bus. Cassini was in orbit around Saturn from 2004 until 2017. The Huygens probe descended through Titan's atmosphere on January 14th, 2005. The Huygens probe was carrying mass spectrometer, which is one of the reasons why we now know how much nitrogen there is in Titan's atmosphere, because we had to send a probe there to directly measure the amount of argon and nitrogen in the atmosphere to finally answer that question. Cassini carried 12 instruments. The Huygens probe carried 6. On both of those spacecraft, it was a combination of remote sensing instruments and in situ instruments, which just goes to show the power of both types of techniques, but also that there's a lot of synergies that we have when we can use both of them together. And so that's about the end of mission. I just want to give you a quick sense, it doesn't show up great, of what tools we had to look at. And this is consistent with the kinds of things that we would like to have for any planetary atmosphere. So this is altitude on the y-axis, or pressure if you prefer it, although there's zero chance I can make everyone in this room happy with one pressure unit. So that's pascals, sorry. Temperature is on the x-axis here, but I wanted to draw your attention over here first. And so what we're looking at here are the instruments that were carried by Cassini, but what I want you to notice is that we're looking at a bunch of different wavelengths. So this is an ultraviolet spectrometer, this is a visible and infrared spectrometer, this is another infrared spectrometer, this was a camera. And so we use these different wavelengths of light to actually sense different parts of the atmosphere. And so we need really broad wavelength coverage, like something like James Webb will have, to actually be able to see this range of pressures in these atmospheres. And so that was one of the things that was so powerful about Cassini. For the first time, we were really able to see composition and temperature in the entire atmosphere, which was really important for understanding the chemistry. And just to note that down here and at the top of the atmosphere, we had in situ instruments carried either by the Huygens probe or carried by Cassini, which flew through the top of Titan's atmosphere quite a number of times. Similarly, you see here the wavelengths of light and where they penetrate to. And so most of the extremely energetic photons in Titan's atmosphere are deposited quite high in the atmosphere. The longer wavelength photons can get deeper in the atmosphere where they can drive some chemistry, which I'll talk about in a minute, hopefully. And then we have some galactic cosmic rays. So on Earth, if you were to walk outside, you'll get bombarded by galactic cosmic rays. They make it all the way to the surface. But on Titan, they don't. The atmosphere on Titan is so thick that the vast majority of the galactic cosmic rays are deposited before they actually reach the surface. And so there's some interesting chemistry that happens there as well that we're just starting to try to sort out. So what happens with all of this? We start with methane and nitrogen. They get broken up high up in the atmosphere, ionized, dissociatively ionized, form some radicals. Those things react together to form all kinds of stuff. In the upper atmosphere, we're forming a lot of things that with triple bonds. So that's where most of our hydrogen cyanide and acetylene are made. Those get transported downward. There's some heavy ions, which I'll show you in a second. That is not relevant for this talk. Deeper down in the atmosphere, the longer wavelength photons that weren't really driving any chemistry higher up because they were not being absorbed by the molecules get absorbed by the things that were made high up in the atmosphere. So the acetylene that was made at the top of the atmosphere then absorbs FUV photons at the bottom of the atmosphere. And it's interesting because this actually results in photocatalytic destruction of methane. And so when those molecules, especially acetylene, get photolyzed, they form really reactive radicals like C2H, C3H, depending on the molecule, that will then go and find a methane and steal its hydrogen away from it. And so this process just goes back and forth, resulting in the creation of ethane. And so deep down in the atmosphere, the methane gets destroyed too, not directly by photons, because those photons are gone, but indirectly by molecules that were created through photochemistry high up in the atmosphere. A lot of these molecules eventually condense, and so we see a number of different types of clouds in Titan's atmosphere. The methane clouds that we knew about from remote sensing from the 1990s, but also a number of other species have been discovered in the condensed phase from Cassini observations, things like hydrogen cyanide, acetylene, propane, ethane, probably mixtures of all of these things. And so there's a lot of stuff going on in Titan's atmosphere in terms of chemistry. A couple of things that I wanted to mention, though. So remote sensing is amazing, and we've learned so much from it. But one of the big things I would say that we learned, and is an important lesson for people who are thinking about atmospheric chemistry, is that there were a lot of things that we didn't have the ability to see that turned out to be hugely important for understanding Titan's atmospheric chemistry. So this is a model of Titan's atmosphere as it would look from in a mass spectrometer prior to Cassini. So using everything we knew from Voyager, state-of-the-art atmospheric chemistry models, this is what we thought a mass spectrum in the top of Titan's atmosphere would look like. These are the actual mass spectrum data. And if you look at the black lines, they actually match pretty well with the orange lines where they exist. But there's a bunch that are missing entirely. I've highlighted some here with the gray arrows just from this one group. Those of you who are used to looking at mass spec might immediately realize what the problem was. But these are all nitrogen-containing ions. And so we really underestimated the role that nitrogen plays in the chemistry of Titan's atmosphere. And the only way we found that out is by actually going there and measuring these things that we didn't know existed. And so this has really informed the models of atmospheric chemistry that we're using for Titan, but is a really important lesson. Another really important lesson is something that came from an instrument that wasn't designed to do this, which is the Cassini plasma spectrometer, which was designed to measure like energetic electrons in the Saturn system. And when they flew through Titan's atmosphere, they started seeing something really weird. So I mentioned that benzene was the heaviest molecule that was detected prior to Cassini, so C6H6. So if you had made a mass spec, in fact, I just showed you one a second ago, that you would have thought Titan's atmosphere looked like, you might think it would go up to 100. And in fact, that's what the instrument was built to do. I just showed you data from that instrument. But CAPS saw something else. So it's still mass to charge on the x-axis now, although we're on a log scale. And so the Cassini plasma spectrometer discovered that there are ions, negative ions up to 10,000, a mass to charge of 10,000, positive ions with a mass to charge up to about 1,000, very high in Titan's atmosphere. We're at 950 kilometers above the surface here. The mean free path in this region of the atmosphere is something like 1 kilometer. So I was really struck by one of the speakers this morning who said that, you know, you have these expectations and then nature just goes off and does its own thing. And I think this is just another example of chemistry that absolutely should not be happening based on anything we understood before Cassini is clearly happening. And so this has really changed our understanding. Oh, just to give you a sense of scale, this is maybe the wrong audience for this, but there's benzene. This is what happens when you spend a day trying to get ChemDraw to draw something that weighs 10,000. I realize that's not a real molecule. My apologies. This is like the world. I had this panic moment where I'm like, oh my gosh, I'm going to show these people this molecule that I drew. But it turns out to be really hard to get any of the programs to draw a molecule that big, and ChemDraw was the only one that didn't crash every time I tried to do it. So just to give you a sense of scale of how wrong we were. And so this has really changed our understanding of aerosol formation. And this is a cautionary tale that I'm going to emphasize in a second. There's one more cautionary tale about the need for in situ observations to go along with remote sensing. I mentioned this discovery of carbon monoxide from Voyager, and as soon as they found it, people started looking at the chemistry models of Titan's atmosphere, and they couldn't reproduce the amount of carbon monoxide. And so that was a problem that we had from the very beginning of the Voyager era, from the early 1980s, up until I started grad school. So I was born after the Voyager-Saturn encounter. So my entire life, up until I became a scientist, this had been a problem. Where is the carbon monoxide coming from? Nobody could figure it out. Well, it turns out that there's O+ ions flowing into the top of Titan's atmosphere that come from Enceladus, the tiny moon of Saturn that's shooting water out of its south pole. And when we figure out where those oxygen ions are actually deposited, they're deposited in the same region of the atmosphere where these other ions are, so that's interesting, although we don't know what it means yet. I'm going to not show you these slides because I have one more thing I want to say at the end. But to suffice it to say that if I were to show you these slides, hold on, we'll get there. One of the things that we figured out, without going into gory detail, is that the only way, and my apologies, we have a Mac to PC situation going on here. One of the things that we figured out is that the reason we couldn't explain the chemistry was because we didn't know about the oxygen. And once you use that oxygen input to the top of the atmosphere and put it into a photochemistry model, lo and behold, the answer pops right out. And so we were never going to figure out the answer to this problem from remote sensing data alone because we just didn't have enough information. And this is my cautionary tale to the exoplanet folks that I work with and talk to, and they really don't like having me around. That was just showing that. One of the other things that we're really excited about thinking about is what this means for the other molecules that might be in Titan's atmosphere. So laboratory experiments, including some that I have been a part of or run in my lab, show that we can make purine bases, pyrimidine bases, a lot of the biological amino acids, either through gas phase chemistry or chemistry that might be occurring on the grains that we produce in these experiments. And so we're really interested to know if these molecules are also being made in Titan's atmosphere. But unfortunately, we can't see them with remote sensing. A lot of people have alluded to this issue. The bigger a molecule gets, the more the signal gets spread out because of the different ways that it can bend and rotate and vibrate and all these things. So the larger a molecule is, the harder it is for us to see in an atmosphere. And the mass spectrometer didn't have good enough resolution to look for these molecules. And so we have to wait for another mission to be able to look for them. And finally, I just wanted to emphasize, I feel like you actually couldn't have given a talk today without talking about how amazing ALMA is. So I don't know if Jonathan's going to mention ALMA at all, just to sum it all up. But even with a spacecraft in the Saturn system, we physically sent something there. There were 5 molecules discovered using ALMA data while Cassini was in orbit around Saturn. And the thing that's even more incredible about this is that every single one of these molecules was detected in calibration data for ALMA, because Titan is used as a calibration target all the time. And even though it sometimes only looks at Titan for a few seconds, ALMA is so powerful that even those few seconds were sufficient to discover a molecule we'd never seen before. But one thing I want to point out, just to go back to what I mentioned earlier about these synergies, especially these larger nitrogen-bearing species, it would not have occurred to anybody to have looked for them until we had the Cassini data that told us there was this really complicated nitrogen chemistry happening in Titan's atmosphere. And so there's been this really important synergy going back and forth between observations and models and lab experiments, and then having the actual spacecraft there to show us things that we can't see otherwise. And then I'm just going to end here. I think I always like to start out telling everyone how unique and exceptional Titan is, and we've recently learned something that makes me think maybe Titan is not an exception and maybe it's actually the rule. So this is Cassini-Sears data of Saturn. And looking in the infrared, we see a lot of these same molecules we see from Titan. We see acetylene, we see ethane. Saturn's atmosphere also has some interesting chemistry going on. I will use the word crash, Reggie. When we crashed Cassini into Saturn, this is what the mass spectrometer sent back. And so it's not just a matter of the simple hydrocarbons that we knew about from remote sensing data from Voyager and from Cassini, but there are also extremely complicated molecules that are presumably organic in Saturn's ionosphere. Unfortunately, the instrument that found the extremely heavy ions in Titan's atmosphere was the only instrument on Cassini that was not functional at the end of mission. And so we don't have comparable data from that instrument of Saturn's atmosphere, but we do know now at least that Saturn's atmosphere is also very complicated, and it's something that we would not have been able to figure out from remote sensing. And now I'm going to stop before she stands up and... Oh gosh, let's see. I can't do the number on the fly, but like I said, the Titan measurements that I showed, the mean free path there is about a kilometer. The region of Saturn's atmosphere that we're in now is, with these measurements, is identical to the part of Titan's atmosphere that we were looking at in terms of density. We wish we could have gone deeper for Saturn like we did for with Galileo probe, but Cassini wasn't designed to be a probe, and the actual end of mission was when the 9-meter magnetometer boom broke off, because then they couldn't point anymore. So the pressure is still extremely low. I don't actually know what it is off the top of my head. I would have to look. I think in mean free path in this particular case.
I guess the atmosphere is predominantly methane.
Predominantly nitrogen.
And then methane is the next dominant
Yes.
species.
Yeah.
So the atmosphere would be net reducing, not
Yes.
oxidizing.
Yeah.
Yet you're seeing things like nitriles that are oxidized species. Why don't you see reduced species?
It's an interesting question. We're still trying to sort out some of what's happening with some of the functional groups. So there were some molecules that we would have expected to see that we don't. One of the classes of molecules that we see very few of are amines. The only nitrogen species that we see that's all the way reduced, or that's mostly reduced, is ammonia, and the abundance is extremely low. And so that's one of the things that we're still trying to understand. The one thing to know, and not to step on, I don't think he's going to talk about Titan. Jonathan, you're not going to talk about Titan, are you? So the one thing to keep in mind about Titan is that because it's so small, the hydrogen that is liberated from all of this photochemistry is escaping. And so Titan's atmosphere is becoming more oxidizing over time. That's actually true of the process that every planetary atmosphere takes as it evolves, because hydrogen is the easiest thing to lose from escape. And so Titan's atmosphere is moving in that direction over time, but that still doesn't explain to us why we're not seeing some of the nitrogen species that are pretty saturated. We still have a lot of questions.
So I guess you've already alluded to it in one of your slides, but I guess Titan has a good kind of physical environment for aerosol formation. So what kind of what kind of composition would aerosols be on Titan, and what kind of chemistry do you think they facilitate?
Yeah, those are two really good questions. So we do tend to think that this may actually be one of the most ideal atmospheres for haze formation, which is maybe a ridiculous thing to say since it's so incredibly hazy. You're almost stating the obvious. But one of the things that we learned both from Cassini and from lab experiments is that it turns out that molecular nitrogen plays a really important role in the chemistry that's happening on Titan's atmosphere. And in particular, it really seems to facilitate haze formation. So if you do experiments in the lab and you only use methane and irradiate methane, you actually don't get as much stuff as if you use mixtures of nitrogen and methane. And so the nitrogen is really important. In terms of the actual particles on Titan, the Huygens probe carried an instrument called the aerosol collector pyrolyzer, which was supposed to collect particles, 2 different regions of Titan's atmosphere, pyrolyze them, and send the results into a mass spectrometer. This is one of the areas of Titan science where it's very easy to get people yelling at each other about what happened with that instrument. The results either make sense or don't make sense depending on which side of the issue you fall on. I tend to think that the main thing we learned from the results is that there is a lot of nitrogen in the aerosol. And that's consistent with a lot of laboratory experiments that have shown that nitrogen seems to be preferentially partitioning into the solid phase rather than the gas phase, which might actually partially answer Mark's question about this lack of reduced nitrogen species, is that the nitrogen seems to be getting pulled into the solid more efficiently, and that may have some explanation. I would really, really like to know what's in those aerosols very badly. That's like the one question that is like closest to my heart. But unfortunately, we don't really have any good data. And from remote sensing, we don't see much of interest. They're organic, which we kind of already figured out. But because they're complex organic solids, remote sensing isn't a great tool for trying to figure out what they're actually made out of, unfortunately, which is another reason that we should definitely send a dual quadcopter there. Yeah, we have a bunch of information about the sizes. Our best size information comes from an instrument that was carried by the Huygens probe called the Descent Imager Spectral Radiometer, which was specifically designed to try to answer that question. And so at each region of the atmosphere, when it was descending, it looked up, it looked down, it looked directly towards the sun, which you're definitely not supposed to do unless you're specifically designed for it, to try to figure out number, density, sizes, and also try to maybe figure out something about the morphology. And so we know now a little bit about the size distribution. We also know deep in the atmosphere the haze particles are fractal aggregates. Higher up in the atmosphere, we don't know as much about size distribution because size and number density are degenerate. When you're looking at remote sensing data, for the most part, in a specific region, we can't tell the difference between having more or having bigger over a certain wavelength region. And so we don't have a lot of information above the region where the Huygens probe's instruments were operating, which is about 130, 140 kilometers and up. We don't have a lot of information. But if you make an assumption about size, you can get number density or vice versa. But again, another place where you really need an in situ tool to be able to answer that question. Okay, I think we need to. Awesome. Do you want